So we've got a couple of different tanks, and what's happening is we calculate steady state first. If we simulate the system just for that steady state, and let me just go through that. So if we go through this and we change the way that we describe the A over here. In the dynamic simulation that we were asked to do, we had this if over here that said if t is less than or equal to 0, it's 1, and otherwise it's 1.5. I'm just going to keep it 1. Okay, and what our expectation is that if we simulate that and we plot, now it looks as though that's changing until you see that these axes have been scaled by 10 to the minus 12. Okay, so basically what we're looking at is flat curves, right? So everything is just staying exactly the same. Let me just make that a lot more clear. Right? So that's the result of the simulation. If we just start at the steady state and we run and we don't change anything, then everything stays flat forever and ever, amen. Okay? So that's the assumption, and I want you to understand that in the section of the textbook where they talk about the steady state, they're not talking about the eventual steady state that happens in the future. They are talking about this mythical steady state that has existed forever and ever in the past. That's the first important thing about the nomenclature. So when we talk about this curve, this response curve that we're drawing out, and all of the tank levels are starting at 1, in the math world, this special math world that we are constructing, time has existed forever, the system has existed forever, and everything has not changed forever. That's the math version of this, right? Like it's not real, but it's like infinitely tall, like long rods or whatever when you're solving differential equations. It's like a fiction that makes the problem easier to solve. And so the fiction is, and why we are saying this is another way of saying you need no further information about any events that happened in the past. There wasn't something that, like, there wasn't like somebody didn't put a time bomb there yesterday that's going to, like, something is going to, like, unexpectedly happen that will affect the system in the future. It's a way of saying everything's smoothed out, we start at steady state, everything's flat, and then something happens. And by convention, always the thing that happens always happens at time 0. So time 0 is just everything happens at time 0. There is a little bit of ambiguity, and I'll grant you that you need to understand that, like, different systems resolve the ambiguity slightly differently, which is really about, does the event happen immediately after time 0 or exactly at time 0? Now, I find it personally, the programming gets easier if I imagine that time 0 is still at the steady state, because that allows me to evaluate, for instance, my derivative function at time 0 and get the steady state value, right? This is useful also down the road. I've used just my brain and analytic methods to find the steady state here, but I could have used fsolve to find the steady state, because if you think about it, this function is returning the derivatives. The definition of steady state is that the derivatives are 0. And so I can use fsolve to find the states that make the derivative 0, because that's what fsolve does, is it finds zeros of functions. And so it's useful for me to be able to pass arguments into my functions that give me the steady state values back. And why this is important is I like that to be time 0. If you had made this less than, just a straight less than, you'd have to do something weird like pass in like time -1 or something to get the steady state values, which is just confusing to me. But you will see many references in other systems, and again, there is some ambiguity that you need to be aware of. Some systems choose to say that the input is 0 at time 0. Some systems choose to say that it is the new value at time 0. This is especially important for step changes. So just be aware, in most cases, you can imagine that that infinitesimal difference doesn't make a difference to the way that the response looks. If I solve the equations correctly, it should be indistinguishable. The solution should be exactly the same, whether the input changed at time 0 or like an infinitesimal amount after time 0. But just be aware, time 0 is like a contentious issue. This is especially important when we start using SymPy, because you'll see we use standardized functions where in the SymPy world, that function is undefined at time 0. And this will bite you many, many times. So I just want you to be aware it's not a solved issue. Time 0 is always weird, okay? So, but let me just go through this approach properly. So these are the nomenclatures that we're going to be using, right? We're going to be saying the steady state value is the value before time 0. The actual value in chapter 3 only, we're going to indicate as a normal variable without a prime. Then we're going to go really slowly. This is the training wheels. Chapter 3 is a training wheels chapter. It is unlike the remaining analysis in the sense that it takes a great deal of effort to distinguish between the real variable, this variable which is on this new set of axes which is called a deviation variable. And that's shorthand for deviation from steady state. Right, so the idea is that we started at steady state and then we deviated from steady state, or we perturbed the variables away from steady state. Right, so in other words, if I told you to tell me how much did the level go up after I increased the flow, you would say it went from 1 meter to some new value, and you would say, oh, it went up like by 0.3 meters maybe, okay? That's the change, that's the deviation from the original steady state. And so if we just look at the way these, I'm sorry, that other screen isn't, I mean, all the lights are on, but okay. Can everybody at least see, everybody sees fine, right? If I told you to just look at that graph and say, right, we've got these two axes. This is just like Celsius and Kelvin, right? Like they are the same size. A change in Kelvin is the same size as a change in Celsius, except the 0 point differs. And so here's exactly the same thing. On the original axes, 0 is over here. But on the new axis, 0 is over there. And so simply, if we want to translate those axes, we end up with this idea that obviously h prime is equal to h1 minus h bar. Okay, that's just straight up the normal shifting of axes kind of mathematics. And so we do this mostly because we plan to solve these problems by using Laplace transforms. And when you look at Laplace transform tables, now if you go down to the last part of the Laplace transform table, you will see if I have a second derivative or a third derivative or a nth order derivative, that translates to s to the power n times the Laplace transform of the thing that I'm taking the derivative of. Minus this term over here, which is a very inconvenient term. It's a constant. It arises as part of the integration, but the important thing is to notice that it requires me to evaluate that function at time 0. Now, you'll remember that I said it's like a bit weird always, like time 0. In this context, what we're saying is that if we choose our variables such that they are 0 at time 0, then this term magically falls away. And this is exactly why we go to the trouble of using deviation variables in the first place. This is the entire reason why we do it. There's no other special advantage, but it does mean that every time we do the Laplace transform of a derivative, and you will eventually, this will become like, you won't even think about it, right? Like if I say, what is the Laplace transform of dx dt, you will immediately say s times x, right? It's just obvious. But you will say that because we're going to be doing a lot of that using only this piece of the, we'll be neglecting that piece. Why? Because we will have taken some steps before to make sure that that term is always 0. Right? So making or using deviation variables makes it so that the Laplace transform of derivatives becomes a lot easier to evaluate. Now, the other thing that I also have asked you to commit to memory, the form of the Laplace transform. Not because I expect you to actually use it, but because I expect you to understand what this integral looks like. So the Laplace transform of a function of time is defined as, right? The key thing that I want you to understand is that the Laplace transform is an integral. And that many of the properties that we rely on when we are doing Laplace transforms are consequences of the Laplace transform being an integral more than any special property of the Laplace. Okay? So does everybody understand that if I say this is the definition of the Laplace transform, it should come as no surprise that the Laplace transform of g of t plus f of t is going to be the Laplace transform of g of t plus the Laplace transform of f of t. Can everybody verify that when they see that integral on the board, they understand that the linearity property or the additive property of the Laplace transform follows from it being an integral? All the things you know about integrals also are things that you know about the Laplace transform. Why? Because the Laplace transform is an integral. Similarly, if I multiply by a constant, for instance, right? So what's the Laplace transform of a constant times a function? Well, it's the constant times that Laplace transform, right? Why? Not because it's some special magic about the Laplace transform, but because it's an integral. And we know that if that integrals migrate, or that constants migrate out of integrals, right? So this is why I feel that it is incredibly important to at least know that the Laplace transform is an integral, at the very least. But I feel that it's even important to know the form of the Laplace transform, just because I think that it gives you a bit of insight into why the Laplace transform does what it does. I'll be toning down the amount of background information that I give during lectures on the Laplace transform. There are some notebooks where I go into a little bit more detail. If you are interested of why does the Laplace transform actually work the way that it does? From a procedural point of view, the important points of a Laplace transform in our subject is going to be that if I have some differential equation which describes the behavior of my system, and I'm going to assume that I've done some manipulation up to the point that I've been able to write this differential equation as some kind of difference between the flow rate into and out of the tank. Now, in this particular case, we know that we've got f in as a function of time, right? And so let's say we've got some constant over here which relates the volumetric flow to the level. Another way of thinking about this is that if we started this as a volume balance, there would have been an A over there, right? And so now if we divide that out so that the integral is, or the derivative is by itself, that becomes a constant on the other side. But I'm going to explain this in this way for a very specific reason, because this is the kind of integral or the kind of differential equation that we can solve very easily using Laplace transforms. So once we've written our variables in this deviation form, and once we have taken time to write a differential equation, and just to be consistent, I'm just going to assume that this is in deviation form, it becomes trivial to calculate the Laplace transform of that differential equation, right? Because of the effort that we've spent, let me just move this to a different place. Because we've spent a bit of effort to make this easy, I'd get SH1 of S is equal to K1 Fin of S plus K2 H1 of S. Okay, why am I saying that? The first Laplace transform, this follows from application of the rule that I just showed you in the table, right? So this table over here says if I take the Laplace transform of some derivative of a function of time, I end up with S to the power of the order of the derivative times f of s, which is what's happening over here. So that's going from that derivative to this derivative over here. And all of these are effectively just definitional transforms. In other words, we're going from the function of time. What is the Laplace transform of some function of time? It is that same function of s, or like the same symbol but of s. And so if some of you are kind of looking at this and saying, but wait a minute, what about the primes and what about the capitals and so on? I'm not really very stressed about like introducing capitals. I find the capitals can get incredibly difficult to follow. So you'll see me be very loose about using capitals. I definitely won't ever subtract any marks if you silently move something from a function of time to function of s. I need to know what you've done. So things that I am perfectly fine with, I try really hard initially, like I say in the training wheels chapter, we try really hard to indicate very clearly by using this, which things are functions of time, and by using this, which things are functions of s. But you can imagine that once the training wheels come off, we're going to stop doing that. And so you'll see from chapter 4 onwards, we will no longer take the time to write primes. It will basically be assumed that we're always working in perturbation variables. And definitely if we're doing Laplace transforms, you know every single Laplace expression. There is never, you can quote me on this, I will never write down a Laplace transform that is not for deviation variables. So if you're looking at that and saying, but wait a minute, I'm super confused. You went from the deviation variables to some other variables and they don't have primes. How would I know that those are deviation variables? You know this because it's a Laplace transform. Right? I will never, ever, ever in this whole subject, we will never write a Laplace equation that is not for deviation variables. What that also means is if I only give you a Laplace transform function, if I give you a function of s, I don't have to write it down that this is a deviation variable formula, right? You know it's deviation variables. And what that means is if you want to go backwards, you have to add back the steady state, the initial values that you subtracted to get into the deviation variable world. Now, I'm going to try and hit the main bullet points here, but if you want to go through a little bit more slowly, you will see on the YouTube channel there is a video called the tank system start to finish, where I go through every single part of this slowly for the tank system, all the way from calculating deviation variables, all the way to Laplace transforms, all the way to transfer functions, back through to invert Laplace transforms, and back to a function of time. So I want to just hit the main points here so that everybody at least knows the way that I'm talking about this, right? So once we've done this, we have now an algebraic problem. And if there's one thing that you remember about the Laplace transform, forget about the integral relationship, forget about everything else. Procedurally, what the Laplace transform does for engineers is it allows us to solve differential equations as algebraic equations. And it does this because of this magical property that when I take the Laplace transform of derivatives or integrals, I end up with an expression that is just multiplied or divided by an appropriate number of s's. And so look at what has happened. We started with the differential equation. We now have an algebraic equation, right? Solving for H1 is now trivial algebra. So anyway, I've solved this equation now. I have now an equation of s To solve the differential equation in the specific case, remember from differential equations, there's these two kind of steps in solving differential equations. There's finding the general solution, which is kind of a shape of an equation that at least obeys the equation. If I plug the equation into the differential equation, at least everything works out. And then there's this thing called the specific solution. So I can solve an equation generally, which is what I've done here, but now I'm not able to give you like a number for H1. Our most common change is going to be this thing, which is from the first three lines of the table. So a unit step is a step from 0 up to 1 to look at step inputs. And what that means is, so I now have, that is now for a particular value of the input. Okay? So how do I now find the equation that corresponds to this? I need to do the inverse Laplace, right, which will give me h1 prime of t. Now how do I do that? And you can see that we go through the whole set of how to do this in Laplace in this Laplace transform notebook. Basically, the easy thing to remember is that there's a function called Laplace transform. Okay? And so you do sim_pi.Laplace transform of the thing that you're trying to do the Laplace transform of, and you get a function of S. And then there is another function called inverse Laplace transform, which does the opposite operation. 4 really simple inverses that actually exist on the table, and you'll see that this particular inverse does exist on the table. Does that make sense? Right, so the Laplace transform that we're looking at here is something over S times S minus something, as this Laplace transform over here. And so I know that the shape of that Laplace transform inverse is going to be like this. Now, you will save some time for these really rudimentary ones if you learn how to use the table, because there it's like really, really simple, straightforward. You don't have to take the time to define the variables. I recommend personally that you use sim_pi only for Laplace transforms that do not exist on the table, because pretty much it's always going to be faster to use the table for ones that exist in the table. sim_pi for stuff that doesn't exist in the table. Okay? That then gives us, and I just want to like finish that thought. If you go and plot this equation, which is exactly this kind of shape that we see, right? So if you think about what that means, 1 minus e to the minus at, we start at 1. When t is 0, that starts at 0. And as t gets bigger, this term gets smaller. And so that term goes towards 1. So if we just focus on the shape, it's very obvious that that is a good approximation of what we see on this diagram.